First of all, I would like to make an announcement about the rump session. So please, everyone, submit something to the rump session. The deadline is tomorrow at 2 o'clock, and the rump session will be Wednesday night. And for the session on digital signatures, our first talk will be by Shuichi Katsumata.
I guess I can start then?
Yes.
Okay. Hello, everybody. My name is Shu. This is a joint work with Raphael, Mary, Fabrice, Thomas, and Marco from all these different institutions. And the topic of our talk will be Threshold Raccoon. So let me just explain what Threshold Raccoon is in short. It is a practical 3-round lattice space threshold signature scheme. And this is the first scheme where we don't have to rely on heavy tools like FHE or homomorphic trapdoor functions. And it scales gracefully up to 1,000 signers. So all these parameters, it stays roughly the same for any number of signers, so about 10 kilobytes plus more. And it is compatible with this Raccoon scheme that we presented at the NIST additional post-quantum signature competition. And we do have some implementations in the paper too for those who are interested. So let me get to the background. So first of all, what are these T out of N threshold signatures? And put it very bluntly, it's an interactive protocol to distribute trust. And to be a bit more specific, there's going to be one verification key. And ideally, this is going to be something that's already used in practice. And the thing is, nobody knows this one signing key. And what is going to be done is that there's going to be these partial signing keys assigned to all these N users. And given T out of these N signing keys, we can produce a signature. So that's the functionality. So looking at it a bit more closely, so when a user comes and say, please sign my message M, then any out of these, so in this example, it will be 3 users, but 3 users can interactively sign and produce a signature under this verification key. And the important thing is that this verification algorithm should just be the same as what you would use in practice for this particular VK. So the signer or the user is kind of oblivious that this thresholdization is occurring in the background. And the important feature of the security is that enforceability. And this is a very, let me explain it through this phase. So in the phase 1, the adversary obtains T minus 1 partial signing keys, and it corrupts users. So in this scenario, it can corrupt up to 2 users. And in phase 2, an adversary can specify any signer set S of size T and perform a signing query. And the most important thing is that the adversary can be included in the signer set right now. So it could act maliciously here. And eventually, the adversary will output a forger on an M, which it didn't query in phase 2. And we say it wins if it can produce this. And why do we want to study threshold signatures? So there's several applications of threshold signature that have been used in practice. So distributing key management. So I think crypto wallets will be one of the most prominent examples. And it could also be used in blockchain scenarios. And I'm not really expert on the application side, so if people know anything other than this, please let me know. And the more important thing for, I guess, us, is that there is a NIST multi-party threshold call expected around 2024, this late 2024. And we want to kind of have a working threshold signature scheme from lattices that we can kind of call it practical. So let me talk a bit about these known post-quantum threshold signatures and where we stand right now. So there are works based on FHE and homomorphic trapdoor functions, but these are typically very slow right now. And maybe in the future it could be very optimized, but currently it's not really practical. There's also some Stark-based schemes or sequential threshold-based signatures on isogenies. And there are a lot of nice works that do N out of N threshold signature with key aggregation, or typically called multi-signatures in the literature. But it does not really work for T out of N for the normal threshold setting. So this is where we stand. So we don't have a very practical working threshold signature scheme for lattices. And now I want to kind of shift the focus and try to explain how we can even try to construct this and what people have tried to do and where it fails. So the basic principle is that for any T of n threshold signatures, typically there's going to be some underlying secret sharing scheme. And for this example, let's use the Shamir secret sharing on LWE secrets. So in LWE secrets, the verification key is just going to be one LWE sample like that. And this S is supposed to be short. So that's our LWE secret. And the way we perform secret sharing is that for user I, we just do the normal Shamir secret sharing. So we sample a polynomial f of degree t, and f of 0 is going to be our secret s. And for user I, si, where we evaluate this polynomial on I, is going to be its partial secret key. And importantly, from polynomial interpolation, given t shares from a user of size t, we can efficiently compute this Lagrange coefficient to recover the original secret s. And this will be very important for the later use cases, but this Lagrange coefficient is not supposed to be, it's not small over this polynomial ring. And this will be very important for security later on. So this is something that I would like to highlight. So once we have this secret sharing scheme, what we also need is a linear signature scheme. And for this, we can just use Lubashevsky's signature scheme, which is in lattice, it's basically a lattice-based Schnorr. So what we do is that the signer will sample some randomness R, create a commitment W, and we're going to hash it to get this small challenge C. And eventually, the response is going to be the normal C times S plus R. And I won't get into the detail about rejection sampling, but I will get back to this item 5 later. But basically, just as in Schnorr, this W and Z will form our signature. And the only difference is that this Z has to be short. And this is where some of the yuckiness comes in with lattice-based cryptography. But in general, this is, I think it's very simple to understand what's going on. And the main thing is that this part, the reason why I call this a bit linear is that this is going to be linear in the secret S and then randomness R. So let's create a naive attempt of a threshold, adaptive, the 3-round threshold Schnorr to lattice setting. So in the first 2 phases, there's going to be a commit and open protocol. And it looks a bit complicating, but this is just doing this 2 rounds. This 2 round is simply required to do this commit and open. And without it, it is potentially insecure against the ROS attack. I say potentially because we really don't know if it's going to be, if we can apply the known ROS attack to the lattice setting, but there is no way to really prove this right now, so I'm writing it potentially insecure. But anyways, we commit this W with this hash function, we make this hash commitment, and we open it. And this is the first 2 rounds. And the 3rd round, this is the more interesting part. So we're going to linearly combine the commitments W together. We hash it. And then the response is going to look something like that, where we have this Lagrange coefficient. And let's verify correctness. So using linearity, the response will just be that. And due to the correctness of Shamir secret sharing, we can just turn that into S. So we have CS plus R. And for the commitment W, we just linearly combine it. It's going to be A times R now. And the important part is that when you look at this, this is exactly the original format that we wanted from the Lubashevsky's signature scheme. So this is exactly, it satisfies correctness. And there's this elephant in the room where about this rejection sampling. But we will, in our protocol, we will remove this by increasing parameters using some techniques. And this is the same ideology as what we did with the Raccoon submission. And the effect is that we can remove the rejection sampling by increasing the signature size a bit. But the most important thing about this is that it works very well in the interactive setting, because since there are no more restarts due to this rejection sampling, we don't have to really think about these weird scenarios where some users just outputs bot in line 7 here. So that's the very general template. And obviously the question is this naive template secure? So in the 3-round classical setting with Schnorr, this was proven secure in last crypto. The question is is it secure in the lattice setting? And it's not. And this is why people haven't really, I think, focused on this problem. So I never seen this really documented anywhere, so let me explain why this is going to be insecure. So let's just focus on user I right now. So that's the response zi that a user provides. And the reason why it's going to be vulnerable is that these challenge C, these vector Ri, they're small. And the Lagrange coefficients are large, as I explained previously. And also the important part is that this Lagrange coefficient can be controlled by the adversary to some extent. So this is the informal attack that we can perform. So the attacker is just going to find two signer sets such that this user I satisfies that kind of relation for the Lagrange coefficient, where P is going to be some moderately large integer, still smaller than this modulus Q. And then what's going to happen is that it's going to ask for this signature, partial signature, and it will retrieve the Z1 and Zi prime. And at this point, using standard linear algebra, what you can do is that you can recover this red component over the integer. And this is the reason why this is over the integer is because when you look at all these components, they're all small compared to this modulus Q. So after this, what you can do is that you could recover all the randomness by taking mod P, and that's how we recover S. So once we recover the randomness Ri's, then we can recover the secret Si too. So this is how you can break the scheme. And the reason why it doesn't really work in the classical setting, like for Schnorr, is because when you try to perform this attack, that critical part is going to be over ZP, which is uniform random. And you won't be able to do this mod P and like eliminating or recovering this randomness won't work anymore. And this is the main difference. And this is why it's a bit tricky in the lattice setting, because everything has to be short, and this shortness can be exploited to some extent. So again, the main issue is that the Lagrange coefficient could be large over mod Q, but at the same time, for provable security, it seems that this C times Lagrange coefficient times this Si is smaller than this randomness Ri, which is supposed to be short within the proof. And this is a notoriously known fact in lattice-based cryptography, and there are workarounds, like using 0,1 or -0,1 linear secret sharing, or doing some kind of noise flattening techniques, but both of this are, as far as I know, very impractical, and we did not want to rely on these techniques. So this is where we stand, and I would like to take a bit of time to explain how we kind of overcome this. And this brings us to Threshold Raccoon. So our simple key idea is to mask the partial signature Zi by an additive zero share. And this is going to be very easy to understand, but the intuition first is that so the individual Zi will now be masked by this zero share, so it won't leak anything. But at the same time, when we collectively add them up, it will recover to this normal signature Z because it's an additive zero share. So let me explain it in a bit more detail. So I will explain it a bit later, but let's assume that we can locally generate these zero shares. So delta 1 through delta 5 in this example. We add them up, it's going to be 0. So what we're going to output now is we're going to output a masked partial signature. So all these like new partial signature is going to be the original Z1 plus this masked term. And correctness still holds because when you add them all together, because this is an additive sharing of the value 0, it's just going to turn into 0, and we get the original signature back. And the more important or the interesting part is how do we prove security? And let me try to explain the intuition of the security proof. So we have 5 users right now. The threshold is 3. So the adversary can corrupt up to 2 users. So let's say it corrupted user 2 and 4. So within this proof, the view of the adversary is going to be this. So it's going to be able to view 3 partial signatures right now. OK? And via the correctness of the zero share in the first hop, what we can do is that we can just replace delta 3 by that orange term, and this is just via correctness. And then we can invoke the security of this zero share, and what we do is that we are just going to view this, we're going to transform this delta 1 into delta 1 star, So it's just going to be these random elements for Z1 and user 1 and user 5. And then we're going to just plug it into the middle term, user 3. So what we effectively have done is that we're going to offset these delta 1s by this partial secret key S1 and S5, and just put it into user 3. And this is just like a statistical thing. So this will follow by virtue of the zero share. And at this point, the most interesting thing is that via the correctness of the Shamir secret sharing scheme, the sum of all the honest users' partial secret key can be equally written as the actual secret key minus all the corrupted users' partial secret keys. So what happens is that we can kind of get rid of this Lagrange coefficient, and we can write user 3's partial signature using only the actual secret key S. And all the other parts, like depicted in blue and green, they're just randomness or either public thing to the adversary. So at this point, what happens is that we only need to simulate this C times S plus R3, which is exactly what we would have done if this was a standard non-threshold raccoon signature scheme. So at this point, we can just rely on previous techniques. And this is a bit kind of a simplified proof. So like the actual proof will be a bit more complicated because there's a lot of states going on and there's a lot of consistency issues, but this is the gist of it. And finally, let me explain how to do this, the zero share. It's very easy. So during key generation, we're going to assume that each user shares a pairwise PRF key. And for, let's say in this user 2 example, so user 2 will use its PRF key to create these individual masks by PRF evaluation. And the row mask and the column mask will be this MI minus MI star. And as you can see, if you add all the masks of the column and the row, they're going to be the same. So obviously, when you add up these zero shares, it's going to be 0. So it's that easy. And for performance, as I said, for any value t, we have a fixed verification key and signature size, and it just scales very well. So asymptotically, the signature size is around order 1, and it has I would say it's very in the practical regime. And thank you for listening. So we do have some follow-up works at Crypto that we would like to share in the last, I guess, 30 seconds. So we have 1-2 round threshold signatures from this new assumption called algebraic one more LWE. This one is already on ePrint, so we use a different assumption to make this into 2 rounds. We also have an adaptively secure version of this because what I kind of explained was in the static setting. And finally, we have a verifiable short secret sharing scheme from lattices, and this will get us robustness, which is something that we didn't discuss in this talk. So that's all. Thank you for listening.
So we'll now take questions. Please come up to the mic here so that people online can hear as well.
Hey, thanks for the talk. Do you assume a trusted setup? And if yes, would moving to a DKG create a problem with the PRFs, or could you just do a key exchange to establish those PRFs?
Thank you for the great question. Yeah, for this talk, we didn't focus on DKGs, and we didn't know how to do that back then. But using these verifiable short secret sharing schemes, we can perform that part. And for the exchange of the PRF keys, we can assume that there's a channel between and just send it.
Thanks.
Thanks for the great talk. So partially my question was also answered. So first question, which verifiable secret sharing you are using for this robust version?
Wait, sorry, can you say that?
Which verifiable secret sharing you are using in the second work?
So this is a new verifiable short secret. So I'm not part of this work, but okay. They invent a new one so to work for the lattice setting.
Okay. And so you also mentioned that you don't use DKG, but then how you guarantee that? Maybe this is a stupid question, but how you guarantee that once you add the partial signatures of this qualified sets, is still the resulting answer this still, for example, the parameters are small. They are LW instance, for example.
That will be baked into this verifiability, so we will be able to verify that part too.
But shouldn't the parties also individually prove that this is still, I mean, small?
So that is baked into the definition of verifiable short secret sharing. Maybe you could discuss offline,
Okay,
but
sure. Thank you.
Hi, thank you for a nice talk. Apologies if you already mentioned this, but do you need rewinding for soundness? And if so, can you argue QROM security of this?
that's a great point. So for this scheme itself, we only need to rely on self-targeted MSIS. So if you were in the previous talk, I guess using their work, we can always prove something in the QROM more formally, but it will increase the parameters. So we just went with self-targeted MSIS for this.
All right, that's cool. Follow-up, can you use extractable commitment schemes to get tighter QROM security?
I don't know personally where you would include that, but I think it's always doable with that kind of technique, but it will probably increase something. So
that makes sense. Thank you.
Okay, let's thank the speaker again. So our next talk will be by Benedikt Wagner.
Okay. Yeah, so thank you for the introduction. I'm happy to be here to talk about this new threshold signature scheme, Twinkle. It's an adaptively secure threshold signature scheme, and this is a joint work with Renas Bajo, Julian Loss, Stefano Tesaro, and Chen Zizhu. Okay, so the focus of this work are threshold signatures. We have heard about threshold signatures in the previous talk. Still, I want to recall what they are. And so you start with a public key and a secret signing key. Now the question is, where do you store that secret signing key? If you just store it on a single device, that's a single point of failure and a high valuable target for an attacker. So what you could do is you could split up your secret key into n shares, and then you give these n shares to n signers. Sorry about my voice. Okay, so these n signers could be n different parties, but they could also be just n of your devices. Now, how do we sign in such a scheme? Well, for that we have to know there's this signing threshold T, and it tells us how many parties need to come together to sign a message. So specifically, if you have, say, more than T signers, then they can interact in some protocol and derive a signature. On the other hand, if you have, say, at most T signers, then no matter what they do and how they behave in any kind of malicious way, they can never come up with a signature. Okay, so let's look at this security property here on the right-hand side a bit more closely, and let's try to understand how we formally model this as a security game. So there are typically two ways to do that. The first one is static security. We have heard about this in the first talk. So here the adversary first announces the set of parties that he wants to corrupt. And then, I'm sorry. Then it learns the public key and the secret key shares for all these corrupted parties. And it can then talk to the remaining honest parties in the signing protocol, and in the end has to output a signature. Good. So there's a second way of modeling this, which is adaptive security. And this is much stronger. Here the adversary first learns the public key, and then it can interact in the signing protocol, and at any point in time it can make corruption queries. So it says, I want to corrupt user I, and then it learns the secret key of that user. And of course, it is only allowed to do that up to T times. In the end, it outputs a signature for some message M star. So this adaptive security here on the right-hand side is much stronger, and this will be the goal of this talk. Now, let's see what's already there, and in particular, I want to look at one specific setting, namely threshold signatures in pairing-free cyclic groups. In this setting, there is a family of schemes, which is called Frost, which all achieve static security. So there's, in particular, as Frost 1, 2, and 3, they achieve static security based on an interactive variant of D-lock, which is one more D-lock. And then there was a nice work by Stefano and Cenzi where they got rid of this interactive assumption and achieved security based on D-lock. Now, in the static setting, there was a work last year at Crypto, Sparkle, and Sparkle comes with 2 security proofs in the random oracle model. The first one is for static security from D-lock, and the second one is now for adaptive security based on this interactive one more D-lock assumption. Okay, so that's the first caveat of this proof. It relies on this interactive assumption. And there's a second one, which is a quite unnatural restriction. Namely, the adversary is only allowed to corrupt at most T over 2 parties. So that's a bit weird, right? You set your signing threshold to T, but then if the adversary really corrupts, say, T or T-1 parties, the security proof doesn't state anything. So that was the starting point of our work. So we asked the question, can we have a scheme where we have adaptive security for up to T adaptive corruptions? And ideally, can we get this without using an interactive hardness assumption? So what we did in this work is we present Twinkle. And Twinkle answers these 2 questions positively. So we get security based on the decisional Diffie-Hellman assumption, and we achieve full adaptive security, meaning up to T adaptive corruptions. Good. So for the rest of this talk, I want to sort of make clear what the technical challenges are that we have to solve. And in particular, if we start from this Sparkle scheme that I mentioned before, there are 2 challenges. We have to allow up to T corruptions, and we have to rely on non-interactive assumptions. So in this talk, I will only focus on the first one. If you are interested in the second challenge and how we solve it, feel free to talk to me afterwards or look into the technical overview of our paper. Good. So if we want to achieve up to T corruptions, we first need to understand why Sparkle does not achieve up to T corruptions. And for that, we need to recall some parts of the security proof and of the structure of the scheme. So as I said before, Sparkle relies on this one more discrete logarithm assumption. Just to recall it, it states that there is no efficient algorithm solving the following problem. We start with some random degree T polynomial, f, and then this algorithm gets as input n+1 many group elements, which are exponentiated evaluations of this polynomial. Now, the goal is to find one of these discrete logarithms, namely f of 0, and we give this solver some oracle that he can use to find up to T of these evaluations. So it can query any I that is not equal to 0 and learn this discrete logarithm f of I. And that means if the solver is able to just compute another D-log, then it has T+1 points on the polynomial, and then it can, of course, find f of 0. So that's the one more discrete logarithm assumption. Now let's see how this is used in this Sparkle threshold signature scheme. So again, we start with some polynomial f, and now our public key will be g to the f of 0. Our secret key will be f of 0. And now we split the secret key into shares where each signer I gets f of I. Okay, so that's a standard Shamir secret sharing. Now let's say we want to sign a message M, and we have more than T signers that come together. Now the first thing we should notice is that jointly they have enough information to recompute the secret key. But of course they will not do that. Instead they will interact in some protocol, which I will not specify in this talk. And as a result, they will get a proof of knowledge of the secret key, right? Jointly, they have enough information to know the secret key. They will compute such a proof of knowledge in a distributed way. And this proof of knowledge is then the signature in Sparkle. Good. Now let's see how the security argument or the security proof of Sparkle works. So we have an adversary against Sparkle, and we want to design a reduction that uses this adversary to solve the one more D-log problem. And I will make one simplification here. I will assume that there is no signing query made by this adversary. So in particular, it gets as input a public key, it makes a bunch of corruptions, and then it outputs a forgery. Now, how does the reduction work? Well, it gets as input this one more D-log instance, and then it gives the first group element to the adversary as a public key. Then the adversary will make some adaptive corruption queries, so it will corrupt user I, and what the reduction will do is we'll just forward this query to its own oracle to learn f of I, which is then taken to be the secret key share. Now, in the end, the adversary outputs a forgery, And the reduction will use a technique called rewinding to extract the secret key. And that secret key is f of 0, so the reduction solves one more D-log. Okay, so we still don't understand where this restriction of corrupting at most T/2 users comes from, but we will understand on the next slide when we look at this rewinding a bit more closely. So what the reduction will do is, as I said, it will run the adversary on this public key as input with some random coins, and then it will, the adversary will make, say, TC corruptions, and then it will output a signature. Now what the reduction will do is it will run the adversary again on the same input, but with potentially different random coins. So the adversary again makes TC corruptions and outputs a signature. Now from these two signatures, the reduction will somehow extract the secret key. But the important thing to notice is that here these corruptions are adaptive, so it could be that the set of corruptions in the first run and the set of corruptions in the second run could be disjoint, for example. So that means over the two runs, the adversary makes 2 TC corruptions, and remember, for every corruption, the reduction makes 1 D-log query. So the reduction makes 2 TC D-log queries, but the reduction is only allowed to make T D-log queries, so we get this restriction. Okay, so that's the reason why we have this restriction. The reason is rewinding, and so the goal for us should be to avoid rewinding and get a scheme that does not rely on rewinding. Okay, so I want to talk a bit about our solution, not go too much into detail, but our goal is to avoid rewinding, and recall that this is the structure of Sparkle. So Sparkle signatures are these proofs of knowledge of the secret key. And because it's a proof of knowledge, we want to extract it in the security proof, and that's why we need rewinding. Okay, so we better have a signature now that is not a proof of knowledge, where we can extract a solution to a hard problem without rewinding. And we will do this in the following way. Our signature will just be h to the sk for some element h that is derived from the message. And then, of course, you cannot verify this because of DDH, so we put a proof there. And now the important difference is this is not a proof of knowledge, or at least we don't need the proof of knowledge property here. It is enough that this is a proof of well-formedness of this element pk prime. Okay, so it is sound proof that pk prime has this structure. Now let's see how this works in the security proof and how we can prove security without rewinding. So we have an adversary against this new scheme, Twinkle. It gets as input the public key, and now it outputs a signature. The signature is this pk prime and some proof. We don't know anything about pk prime. We just know the proof verifies. So now we consider two cases. The first is pk prime really is h to the sk, the thing that it should be. Well, in this case, it's a CDH solution, right, for pk and h. So the reduction can just take it from the signature without any rewinding and output this as a CDH solution. Good. Now what about the second case? If it's not equal to h to the sk, well then the soundness of this proof system guarantees that generating this proof and generating the signature is a statistically hard problem, so we don't need any reduction at all. Okay, so now we got rid of rewinding. So what do we have now? What I showed you is a proof sketch from CDH, but I didn't tell you how we deal with corruption queries, and I didn't tell you how we deal with simulating honest signers in the signing protocol. But the proof does not need rewinding, so we can just do the same thing that Sparkle does, namely we add a D-log oracle to our assumption, and then we get a way to simulate corruptions. Because it does not need rewinding, we simulate up to T adaptive corruptions. Now, what about honest signers in the signing protocol? When we wrote our proof, we noticed, okay, our scheme, our signing protocol shares some similarities with Sparkle. We looked at their proof and we found that there's some gap, some adversarial behavior is not covered by the proof. And so we fixed this, and now we get a proof from one more CDH for up to T adaptive corruptions and signing queries. Okay, and the next step, and I will not talk about this, is how to replace one more CDH with DDH, a non-interactive assumption. Okay, so let me summarize what we have seen in this work. So we have constructed Twinkle, a new threshold signature scheme from DDH. It is adaptively secure for up to T adaptive corruptions. In the end, I want to mention two open problems. And if you have any ideas, feel free to talk to me afterwards. So the first one is, can we reduce the round complexity of this construction? So I didn't tell you in this talk, but maybe you heard it in the first talk. So this Sparkle scheme has a 3-round signing protocol, and our new Twinkle scheme also has a 3-round signing protocol. So it would be cool to reduce the round complexity, for example, to 2 rounds. The second problem, and I think this is much, much harder, is to get the same guarantees from a search assumption, a non-interactive search assumption, for example, CDH. And I think the reason why it is much harder are the adaptive corruptions. And I think new techniques are needed to solve this second problem. Yeah, and that's all I want to say for this paper. Thank you for your attention.
So do we have any questions?
Nice talk. So I was confused a little bit about the non-interactive assumptions. You said that OMDL is interactive, while one more CDH is non-interactive. How come?
Okay, I think I didn't say that, but okay. I'll explain. Maybe it was confusing. So this is still an interactive assumption. You're right. But we have a way to replace this interactive assumption in the paper in a second step that is somehow isolated from all of the rest with DDH. So let me maybe give some intuition. So we look at our scheme, we write it abstractly using a linear function. So we replace we replace x maps to g to the x with some generic linear function. Our scheme still works and our high-level proof still works for some kind of interactive assumption related to that linear function. And then we find a good instantiation of this linear function for which the one more assumption related to this linear function is implied by DDH.
I got it. Yeah, thank you. Another question, sorry if anybody else. So you said that, so you know that static and adaptive are one class of threshold signatures. Another classification can be TUF0, TUF1, and so on. So if I understand correctly, you prove in the weaker notion of security, what are the main drawbacks for extending your work to TUF1 notion of security?
Okay, so maybe for the audience, this classification is about how much does the adversary learn, or is the adversary allowed to learn about the forgery message? So for example, in our work, and this is actually in many works, we don't allow the adversary to talk to the honest signers for the forgery message at all. But for example, if you have like a non-interactive threshold signature scheme where you just have signature shares, you could also allow the adversary to get, say, up to T signature shares on the forgery message. This is a stronger notion. And as you are correct, we only prove this TS UFCMA 0, where you don't learn anything. We actually discussed this before writing it down. We can achieve some intermediate notion because we have a 3-round signing protocol. I think for the second round, we can give the adversary up to T messages. But I think this is a bit like weird and convoluted, so we just stick with the simpler one. And I don't know how to really extend it beyond that. So I think there's a recent blind signature paper by Stefano. Maybe you can use techniques from that.
Okay, yeah, thank you. So there is a hope for 0.5 notion.
Yeah, something like that.
Yeah, thank you.
Hi, thanks for a nice talk. Simple question. Can you say something about how these schemes compare in terms of efficiency?
So the one more CDH-based variant is, of course, more efficient than the DDH-based one. So the one more CDH-based one is like you have a Schnorr signature and an additional group element. That's roughly what it is. If you now go to the DDH-based one, I think you have 2 group elements and then something like 1.5 times the Schnorr signature. So you have like 5 elements in total. So I think for in terms of the guarantees that we achieve, this is not a big overhead. Yeah.
Thanks.
I have a question as well. I was wondering if you thought your techniques could apply to pre-processing. Like, can you, I mean, not for your scheme because you hash the message, but the techniques in general, do you think would allow pre-processing?
Okay, so yeah, okay, so I don't see how currently. The problem is that in the first round, maybe I can go back to that. So you need to have this element H, which is the hash of the message, and then the parties need to compute this proof interactively, so they should better know this element H in the very first round, so they need to know the message in the very first round. Yeah. That's why we don't have pre-processing, and I currently don't have an idea how to avoid this.
Okay, let's thank the speaker. And for the last talk in our session, it will also be given by Benedikt Wagner.
Okay, thank you. So this talk will be about toothpicks, a new multi-signature scheme, and this is a joint work with Jiaxin Pan. Okay, so let me first explain what multi-signatures are. So you have a group of signers, they all have their public keys and secret keys, and they are generated independently. Now they come together to sign a message, they interact in some protocol, and they output a signature. You can then verify the signature with respect to the list of their public keys, and intuitively, the signature certifies that all of these signers participated in the signing and gave their consent. So unforgeability says something like this: you can only come up with such a valid signature if all of these signers participated. Okay, let's relate this to the previous talk. You can think of this as an n out of n threshold signature scheme, but with the additional advantage that all of the signers generate their public keys and secret keys independently, and then they can come together and form these groups of signers. Okay, so in this work we look at, again, pairing-free cyclic groups. So this is, again, about schemes in pairing-free cyclic groups, and the second focus of our work is to have a two-round scheme. So that means in the signing protocol, every signer outputs exactly 2 messages. Now in this setting, there are 2 very relevant works. There's Music 2 and there's HPMS. Both have 2-round signing protocols, while Music 2 relies on one more D-lock, this interactive assumption that we have heard about before. HPMS uses the D-lock assumption. And the third thing I have written here is the security bound that we get for these schemes. So here, epsilon is the probability that the adversary breaks the scheme, and epsilon prime is the success probability of a reduction, for example, breaking D-lock. Now, what we observe if we look at these bounds is that they are very loose. So if we interpret them from a concrete security perspective, then let's say we assume a 128-bit hardness for our underlying assumption, then they don't give us any meaningful security level for these 2 schemes. And the reason why we have these loose bounds is rewinding. So we have seen in the previous talk, rewinding leads to problems. Here it leads to different problems, namely a very loose reduction. So what we asked before the last Eurocrypt was the question whether this rewinding is inherent or whether you can avoid it in that setting. And last year at Eurocrypt, Jiaxin and I presented this work called Chopsticks, a 2-round scheme that is tightly secure based on the DDH assumption. Now, let's see what that means in terms of concrete numbers. So what I've written here is the security level that you get from the security bound if you assume that the underlying assumption is 128-bit hard. And what you see is that Chopsticks has still a very high security level, whereas these non-tight schemes, HPMS and Music 2, don't have any meaningful security level. However, what you also see in this table is that we pay a price for that. And that price is in terms of efficiency. So for example, if you look at the signature column, then the signature of Chopsticks is about 5 times as large as the HPMS signature. So the natural next question is, can we avoid this efficiency overhead? And this is what we did in this year's paper. This year at Eurocrypt, we present toothpicks. So toothpicks is like Chopsticks, but smaller. It has 125-bit of security if we use the same assumptions as before. And you see that the communication per signer and the signature size are much, much smaller now. In particular, if you look at the communication per signer, then it's even smaller than for Music 2. So that's our result. Now, for the rest of the talk, I want to explain where this inefficiency in Chopsticks comes from. And then towards the end of the talk, we will see how we avoid it in toothpicks. So this is Chopsticks. This is the work from last year's Eurocrypt, and let's now see how that works. So Chopsticks combines 2 building blocks into a multi-signature scheme, namely a linear lossy identification scheme and a linear dual-mode commitment scheme. Now let's recall what these building blocks are. Let's start with linear lossy identification. And we will start very simple with an identification scheme. So in an identification scheme, we have some prover, in this case Alice, and she knows a secret key and she wants to convince Bob that she indeed knows that secret key. Okay, so what is a lossy identification scheme? In a lossy identification scheme, we have two ways of setting up the public key, and they are computationally indistinguishable. The first one, I would call it the normal mode. So here there is a secret key and you have perfect completeness and everything is fine. And then there's a lossy mode. And in this lossy mode, there is no secret key, and in particular, even an unbounded prover Alice could not make the verifier Bob accept. Okay, so convincing the verifier is a statistically hard problem. And then we also need some linearity property. I will not explain that in detail, but the intuition is that we later want to take multiple transcripts and aggregate them together into a single transcript. For that, we need some linearity property. Now, the second building block is this linear dual mode commitment scheme. So let's again start with a commitment scheme. Alice commits to some message to Bob using a commitment key, and then later she can open this commitment to the message that she committed to. In a dual mode commitment, there are again two ways of setting up this commitment key. They are computationally indistinguishable. The first one is statistically hiding. That means the commitment does not reveal anything about the message, and in particular, there is an equivocation trapdoor that you can use to open this commitment later on to any message that you want. And then there's a second mode, the statistically binding mode. In this mode, the commitment statistically fixes the message. Good, and again, we need some linearity property to aggregate commitments later on, and again, I will not specify that in detail. So now, as I said, these two building blocks are combined into a multi-signature scheme in Chopsticks, and this will also be true in our new scheme Toothpicks. So how can we do that? Let's give it a first try. What we will have is Alice and Bob. Let's say we have a two-signer setting, and Alice and Bob will both have a public key and a secret key for this identification scheme. And then they will also have access to a message-dependent commitment key. Now what they will do is they will interact in some two-round protocol that I would call a committed identification. So roughly what happens is that Alice convinces Bob that she knows her secret key, and Bob convinces Alice that he knows his secret key. And parts of this identification scheme are committed using the commitment key. Now, as a result, they will obtain a transcript, or more precisely, a transcript where parts of the transcript are in committed form, with respect to their public key and this message-dependent commitment key. And by linearity, they can now obtain a single transcript, which is valid for a combination of their public keys and this commitment key, and this is the signature. Okay, so that's our first try of doing a multi-signature scheme. Now, before we look at the security proof, I want to make some observations. Well, the first observation is that in the scheme, of course, there is a secret key, so our public key is in normal mode, and when signers honestly interact with each other, they will, of course, use their secret key to compute this signature, to interact in the signing protocol. Now, what if the public key is in lossy mode? Well, then we observe that if the commitment key is in this hiding mode and there's an equivocation trapdoor, you can still simulate a signer using this equivocation trapdoor. And in the remaining case, the public key is lossy and the commitment key is binding. In this case, generating a transcript is a statistically hard problem. Okay, so looking at these four cases, this suggests the following proof strategy. We could set our public key to be a lossy public key that is indistinguishable from the actual public key. And we could make sure that the commitment key for messages that we have to sign is in hiding mode, so we can sign using the trapdoor. And we make sure that for the forgery, it is in binding mode. So now for the forgery, this is a statistically hard problem. And so we get a security proof without any rewinding. However, notice that if we want to program it in this way, to make sure that the forgery key is binding and all the other keys are hiding, we need to guess the forgery message. So this, again, leads to a security loss. And one of the technical contributions of Chopsticks is to remove the security loss using a technique that is called pseudo-random matching. So here we will again have Alice and Bob, but now they will not have one public key each, they will each have two public keys. And there will also be 2 message-dependent commitment keys. And now what they will do is they will interact in this protocol from before, but 2 times in parallel, using one of their public keys in each one. And to decide which public key to use with which commitment key, they flip a pseudo-random bit. So let's say Alice flips this pseudo-random bit, and let's say, for example, it is 0, then she will use her public key 0 with commitment key 0. And say Bob flips bit b equals 1, then he will just match commitment key 0 with public key 1. Now, as a result, they obtain 2 transcripts, and they use linearity to generate a signature. And the signature is now consists of 2 transcripts for combined public keys and commitment keys. Okay, and this is where the inefficiency in chopsticks comes from. And this, in toothpicks, is the thing that we avoid. So this factor 2 overhead will be avoided. But before we look at toothpicks, let's first try to understand why this gives you tight security. And for that, we look again at the security proof or a sketch of it. So we have the public key for Alice, and we will set up one of the public keys in lossy mode and one in normal mode. And now for every message, we will program one of the commitment keys in hiding mode and one in binding mode. We will do it in such a way such that if we sign honestly, then the lossy public key is matched with the hiding commitment key, and the normal public key is matched with the binding commitment key. So we can simulate the signer using the secret key in one transcript and the equivocation trapdoor in the other one. Now let's look at the forgery. Because we don't want to guess and program the forgery differently, we know that the picture looks like this. And so the only thing that we can now say is that this bit bm star is pseudo-random for the adversary because he didn't query the forgery message. So with probability 1/2, the matching will be like this, and in particular, the lossy public key will be matched with the the binding commitment key. And this generating this part of the signature is a statistically hard problem. So that's the pseudo-random matching technique. And as I said, this leads to this factor 2 overhead. So now let's look at our technique, and I will not give a lot of details here. I will just tell you what we do and not so much how we do it. So as I said before, Chopsticks combines this linear lossy identification scheme and the dual mode commitment scheme into a multi-signature scheme using this pseudo-random matching technique, and this technique leads to a factor 2 overhead. We have 2 transcripts in the signature. The communication is now 2 times as large as this very first scheme that we have seen. Now what we will do in toothpicks is we will introduce a new technique that is called pseudo-random paths, and this will result in just having one single transcript in the signature and in the communication. And then we have an additional trick, and this trick is to weaken the binding property of this linear dual mode commitment scheme. So in some sense, our commitment scheme is now no longer binding. What we get from that is a more efficient instantiation of this commitment scheme. Now you may ask, okay, well, how can we use a commitment scheme if it's not fully binding? Well, we observe that these linear lossy identification schemes, which are also used in other places in cryptography, have actually a very strong lossiness property that was unobserved before without any change. So we prove that for any linear lossy identification scheme, and this stronger lossiness property compensates for the weak binding notion of our commitment schemes. Okay, so that's an overview of what we do in this work. Now let me summarize. We presented toothpicks, a new multi-signature scheme. It is a 2-round scheme. It is based on the decisional Diffie-Hellman assumption and is tightly secure. And the important thing, it's much more efficient than this chopsticks scheme with the factor 2 overhead that we have seen. The techniques are these new pseudo-random paths technique and more efficient commitments. And now I want to mention one open problem in the end, which is, can we have a scheme that is tightly secure and supports key aggregation, meaning that you can take the list of all public keys and you can aggregate them together into a single short public key. So the very first template that I've showed you that does not use rewinding but is not fully tight actually supports key aggregation. However, the tightly secure scheme with pseudo-random paths and pseudo-random matching does not support key aggregation. So I think this is a very interesting and challenging open problem. And that's all I want to say. Thank you for your attention.
So do we have any questions? So I have a question. Do you think you can combine your lossy ID and commitment scheme to apply to a 2-round threshold scheme?
Lossy ID and the commitment scheme?
So your technique of combining the lossy ID and commitment, either in chopsticks or toothpicks, I guess.
Yeah.
Do you think you could build a threshold scheme?
I think if you only look at static corruptions, that should work.
Yeah.
I'm not sure how interesting it is if you only look at static corruptions. For adaptive corruptions, we actually have a paragraph in the Twinkle paper why this probably doesn't work. So the reason is that if you have if your global public key that represents the set in the threshold signature scheme is in lossy mode, then there is no secret key, and that means for at most T of the secret key, of the public key shares, there can be a secret key. Otherwise, if you have more than T public key shares for which there's a secret key, you could interpolate the secret keys and get a secret key for the actual public key. So you kind of need to guess in advance what is the set of T parties that the adversary will corrupt, and that's not possible if you have adaptive corruptions.
Okay, thank you. Are there any other questions? All right, then, let's thank Benedict and Shu for the wonderful talks. And that concludes the session.